Hi, thank you so much for joining me as we delve into thermodynamics. It is assumed at this point that you are familiar with delta H naught of a system or the enthalpy. Most Chem 1 students will be introduced to that in terms of exothermic versus exothermic processes. What we want to look at now are the twin concepts of entropy in the context of the laws of thermodynamics. The zeroth law of thermodynamics says that heat flows from a high temperature system to a low temperature system. At high temperature, you have a lot of kinetic energy. Via collisions, that kinetic energy is transferred to the slower moving molecules until we reach what's called thermal equilibrium. Okay, the first law of thermodynamics says energy can be neither created nor destroyed. However, it can be converted from one form to another. For example, chemical energy can be converted into electrical energy. Mechanical energy can be converted into electrical energy. So we can have transformations of energy, but the first law of thermodynamics said ultimately energy can be neither created nor destroyed. The second law of thermodynamics is what introduces this concept of entropy. Entropy, given the symbol S or S naught under standard ambient temperature and pressure, is a measure of the order or freedom or energy distribution or probabilities of arrangements. So the more you can rearrange and arrange things. So each rearrangement is called a microstate. So the more microstates you have, the higher the entropy. I like the idea of freedom because it's a very positive thing for young people to have more freedom in their life. So changes in entropy that are positive are considered favorable. So positive entropy changes for a system is a favorable process. Okay, in other words, it wouldn't be the entropy that would be a barrier for the process to proceed to make lots of products. I usually say make buckets of products under those conditions. Okay, so that second law of thermodynamics says that in any spontaneous process, there is always an increase in the entropy. But here's the issue. It's the entropy of the universe. That's not as readily measurable in a laboratory situation. So we're going to be looking instead at a system and the entropy of a system and defining spontaneity based on the system rather than dealing with the universe. Okay? But you do need to know your laws of thermodynamics. We're not going to disobey those laws. Okay, now the entropy of a perfect crystal at 0 Kelvin is 0. Now, this is an interesting concept. For enthalpy, you may or may not have noticed, we always had a delta in front of it. It is possible for entropy to not have a change. In other words, a system has a positional entropy as it is sitting at that state. It doesn't have to be a change to be measurable. Each system has its own positional entropy. And we will see that gases have the highest entropy. They have the most freedom. They can rotate, they can vibrate, they can translate. They have a lot of freedom, and because they have a lot of freedom, the molecules can be arranged in many different ways and so forth. Much more disorder. Solids have the fewest degrees of freedom. They can vibrate, or atoms can just twitch in place, unless, of course, we have a perfect crystal at 0 Kelvin. Okay. Now, what you want to, as you're looking at increases in entropy or decreases in entropy, always check states first. Okay. Once you've checked states, we can look at things like mixtures, whether we're going from pure to mixture, or we can look at moles. like more moles of gas would have a higher entropy, for example. Okay, but always look at those states first as we're evaluating. An increase in entropy would include dissolving. In this case, you are taking, say, a solid, possibly in something like water, and you're having to move apart the water molecules and break apart the solid molecules. That is typically going to be a positive entropy change. Gases expanding, solids going to liquids, going to gas, are all examples that are a positive delta S, or an increase in entropy for a system. Now let's take a look at this. Let's choose the substance with the higher positional entropy per mole. Okay, if it's a liquid compared to a gaseous, hands down the gas is going to win. Okay, especially much more vibrational and translational. Translate means to move through space. Vibrate is when you have two atoms and they can vibrate back and forth. You can think of the bond as a spring, and they can stretch out or they can push in. That would be a very simplistic look. The bigger the molecule, the more possibilities of that movement. Okay, oxygen gas at a high pressure compared to a low pressure. Gases are going to have much more freedom at low pressures. Think of it this way. The higher the pressure, as you increase pressure, you're ultimately going to go from a gas to a liquid and possibly to a solid, and that's a decrease in entropy. So the higher the pressure, the more likely it is that we will decrease it. So that high pressure, okay, would have the lowest positional. The low pressure is going to have the greatest delta S, or greatest S naught. Okay, two separate 1 liters, so pure versus a mixture, the mixture is going to win. Okay, because if all I have is nitrogen, there's only one way to arrange that: nitrogen, 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 nitrogen. But if I throw oxygen in there, I can have nitrogen, oxygen, nitrogen, nitrogen, oxygen, oxygen, and you get the idea. Hundreds of ways that we could arrange those gas molecules. So typically, a mixture is going to have higher entropy than our pure substances. Okay, so now let's predict some signs of changes. We go from solid to aqueous. Aqueous has much more freedom. These ions are swimming around in water, so a lot more freedom than when they're bound into a lattice, so that's positive. I have a gas plus a liquid going to aqueous, so I'm trapping my gas. I'm going to predict a negative delta S for that, and a negative delta S naught. I've got gas, 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 so I've got all gases, but I have 3 moles going to 2 moles. That's going to be a negative delta S. Check the states first, and once they're all the same states, then you can look at moles. Here we have aqueous ions making a precipitate, a solid, on the bottom of a beaker. That's going to be a negative delta S naught. Okay? Now, just one more thing that I want to mention right now, and that is how you calculate. The change in entropy of a universe is the system plus surroundings, and we can get a measure of the surroundings by taking the enthalpy over the temperature. Okay, so if we had this one, we're at 25 degrees Celsius. Be careful. The only time you can use degrees Celsius is with a delta T. If you have a T, you need Kelvin. So in this case, I'm going to take that 2, so it's going to be minus 286,000. I'm going to get it to joules. You'll find that entropy is typically in joules, enthalpy is typically in kilojoules. So be careful. Over 298 Kelvin. and we should get 960 as our answer for the change in entropy of our surroundings. Okay, so that would be it for this segment on entropy and the laws of thermodynamics. Thanks so much for joining me.